Okay, welcome to the NUPOC video study guide number 67. We're finally going to get into some physics problems, starting with statics. And of course, statics is where we have no acceleration, so we have no net force in our system. So we're either looking at systems that are at a constant velocity or at rest, which is the case in this problem, where we are looking at a mass sitting on an inclined plane. And that inclined plane is inclined to some angle theta, right, above the surface here. And at some point, right, at some theta, the component of the gravitational force that's dragging this mass down the plane, right, is going to overcome the force of friction holding it up, and the block is going to start sliding down the plane. And so we're interested in at what angle theta does that block begin to slide, right? So this is a very basic problem, and I'm sure a lot of you people have done this problem many times. You can probably work through it pretty quickly, but it's worth stepping through in some detail to make sure that we understand why we're making each step in the problem, or why we're taking each step, and address a couple of kind of follow-up questions that could come up that an interviewer could throw out there. So the first thing is, since we're going to be dealing with vectors in this problem, and in just about every physics problem, right, and in a lot of other problems, engineering problems, whatever, we want to start by picking a coordinate system. And this is actually a question that an interviewer would, could throw out there. That you could get halfway through the problem, and you're kind of doing it right, but they might say, well, what coordinate system did you pick? And maybe you didn't even think to pick one, right? And so you're kind of floundering around trying to figure, well, what exactly coordinate system fits the work that I've already done, right? And fits all the positive and negative signs and all the forces that I've already put in there. So it's important to set up your coordinate system first before we start doing the math. So of course, since we're dealing with this plane here, we're dealing with forces that are parallel to this plane, and of course forces that are normal to this plane. And so we want to make sure we pick a coordinate system that's convenient for dealing with those kinds of forces. So let's pick a coordinate direction, or a unit vector direction parallel to that plane, and let's call that x hat, and we'll pick a direction normal to that plane, and we'll call that y hat. Okay, and of course we have a z hat as well if we use the right-hand rule, right, crossing x into y into the page, but we're not going to use that in this problem. Okay, so the next thing, since we have a statics problem, we want to look at what are the forces acting on the block. So let's kind of take the block on its own and draw a free body diagram, right? Let's just look at the block just to simplify, right? So we have this block floating out here, right? And we have a force of gravity. That's one of the big assumptions that makes this problem work, right? Is that we're in a gravitational field, and it's pulling directly down on the block, right? And so this, I'm going to call this Fg, and it is a vector, but I'm going to say its magnitude is mg, right? And of course it has two components, right? It has a y component and an x component. So this is the component acting in the minus y hat direction, and this component is acting in the positive x direction. Now, of course, it's just as valid to say that this force vector, we can slide this vector, since we're not dealing with torques and moment arms and stuff like that. We can slide this force over here and slide this x force up here, so we have something like this, right? And that's just as valid, right? So let's go ahead and use kind of this, let's use this convention where we have, I'm sure you may have heard of, when we're dealing with vector addition, you can have head-to-tail or tail-to-tail convention. So let's actually use the tail-to-tail convention, where instead of looking at this vector and then this vector added to it, or this vector and then this vector added to it, let's just look at this vector, right? Let's look at the x component here emanating from the center of the block, and the y component here emanating from the center of the block, right? So let's go ahead and draw those on our free body diagram, right? So we have this, and let's call this Fy, and we have this force here, and let's call that Fx. And we can see from these sort of triangles that we've drawn here, See that this is going to be theta, and we'll get to how to show that in a minute. This angle right in here, that's theta if this angle is theta. And of course, by the alternate interior angle theorem, I think that's what it's called, this angle is also theta. So now that helps us determine what Fy and Fx are if we know that the magnitude of Fg is mg. So Fy, we can see, is acting in the minus y hat direction, and it has a magnitude of mg cosine theta, right? If this is theta and this is Fy. And we have Fx over here, and that is acting in the positive x hat direction, and it has a magnitude mg sine theta, right? If again this is theta here and this is Fx. Okay, so what other forces are acting on the block? Well, we are interested in the point when it has when it just barely starts to slide. So it's really at rest. It's just barely starting to move. So at that instant, right? There's a force. There's a force. The force of friction, right? Holding that block back up. That's just barely being broken by Fx. And we also have a normal force, which is the plane, the inclined plane, pushing back up on the block, because the block is not accelerating through the plane. It's not accelerating in this direction. If there's no acceleration in a direction, then there must be no net force in that direction, which means there must be an equal and opposite force balancing Fy, and so let's call that Fn for the normal force. And we can say that the normal force then is in the positive y hat direction, and it has magnitude mg cosine theta. And now we can look at the friction force, which is simply mu, the coefficient of friction mu, which is just a scalar between a unitless scalar between 0 and 1. And Ff is just the coefficient of friction mu times the normal force. And of course it acts in the minus x hat direction. So this will be minus x hat mu mg cosine theta. Okay, so like we said before, we are interested in the instant when this block just barely begins to slide and what the angle is when that happens. So when it just barely begins to slide, Fx has just barely overcome Ff, and so we can essentially say that Fx equals Ff, or that is, there's no net force in the x hat direction, right? When the block begins to slide. So let's go ahead and look at the sum of forces in the x hat direction. Okay, well, in the x hat and minus x hat direction, right? Anywhere along that plane. Okay, so we have Fx, and that's in the x hat direction, and it has magnitude mg sine theta. And we also have this Ff, and that's in the minus x hat direction, and it has magnitude mu mg cosine theta. And we said there's no net force, so when we add all the forces together, right, it equals 0. Okay, so now we can cancel a bunch of things, which is really nice. We can divide both sides by x hat mg. That gets rid of an x hat, an m, and a g in both of our terms. We can then move our mu cosine theta to the other side, and so we end up with sine theta equals mu cosine theta. And of course we can bring the cosine theta to the other side. Well, we can divide both sides by cosine theta, which will give us sine theta over cosine theta over here, which is just tan theta. So we can say that mu equals tan theta, or theta equals the arctan of mu. And so that is the angle at which the block will just barely begin to slide. And in fact, it's independent of the force of gravity, or the gravitational acceleration. It's independent of the mass. So it's actually kind of counterintuitive. It's only dependent on mu, right? So if we have a higher mu, right? If we have a higher mu, the block will sort of stick to the plane up to a larger angle, and for a lower mu, it will start sliding at a smaller angle. So one of the follow-up questions, or question that might be sort of, could be asked as you're going through it, certainly to see if you understand the fundamentals of physics and math and things like that, besides just considering the coordinate system and making sure you carry your unit vectors through, is, well, how do we know this angle is theta here? If this angle is theta, well, how do we know that angle is theta? I know we said we know that these two angles have to be the same by the alternate interior angle theorem, but what about, how come this angle is theta and this angle is theta? Well, let's start by redrawing our smaller version of our original inclined plane, which is a triangle. Now let's go ahead and extend all the sides, right? So we have a bunch of intersecting lines like this, and we know this is theta. Okay, so here we can say that if this is theta, and we know this is 90 degrees, and we know there's only 180 degrees in a triangle, well then this angle here must be 90 minus theta degrees. And now, since we're interested in an angle between the plane and a, well, I guess the angle is actually between a line that is perpendicular to the inclined plane surface, is between this line that's perpendicular to the inclined plane surface and this vertical line. We can go ahead and just draw in a line, right, that is perpendicular to the plane surface, and we can draw it wherever, it doesn't matter, and then we could draw a vertical, but we already have a vertical line here, so let's just draw it right there, okay? And we know that this is 90 degrees because we know it's perpendicular. We drew it to be perpendicular to the surface of the inclined plane. And of course, by the vertical angle theorem, we could also say that this is 90 degrees, but what we're really interested in is this angle here. Well, we can say that along this straight line, right, if this is a straight line, then going from here all the way to here, right, this is 180 degrees, right? It's a completely flat line, right? And that's one of the only assumptions you can make from a drawing in geometry, if I recall. And so if you have this angle as 90 minus theta, and this is 90 degrees, well then, to make that whole thing 180 degrees, this angle must be theta.